All right. I think the audio is working. Hello and welcome back, everyone, to my wonderful little game engine stream. Making something with Vulkan. Those questions that people keep asking. Last time we added bindless textures to the system. So there's a few more things to be done for complete like the set of bindless things that are available right now. But instead of going that way, we will first get models loaded into the scene. And in doing so, we will be able to sort of see what data we need before we optimize it. For textures, I know that as there's no other way of doing it. So let's get started then. First things first, the format that I will use for the models is known as glTF. That's GL transmission format. I forgot the browser. Yeah. This GL transmission format. Okay, let's check actually. glTF. Yeah, GL transmission format. So it's a open source format that exists. It's mostly built for transfer of assets, which means applications like digital creation content creation applications like 3D Max, Maya, Blender, these can create author glTFs, and then we can use it in other places, right? This is built to be a runtime model. So in the sense you can directly use glTF models and they're more or less, let's say, not optimized, but focused towards giving you a decent format for that. Of course, most production engines tend to use it as just a intermediate format that will convert into whatever their format is, right? Because this is the general solution for solving everybody's problem in a decent enough way. Most game engines have a very specific problem and they want a very specific solution to it. So, you know, anyway, for the interchange, at least glTF is very well written. And the spec is well defined as well. So we can look into this to read the spec in detail or use a quick reference. End of the day, all glTF is stored as JSON or as binary files. In this case, we will be using binaries, but we can look at some JSON samples, looking at glTF samples. So was the Chronos group glTF samples archived? That's the new one. Okay. So glTF sample asset, you can go to models and look at all of these, right? So there's binary, there's a GLB file. I prefer those because then you have to move around. But this is a default glTF. As you can see, it has JSON with accessors. Accessors are a thing that I'll explain later. But it's basically just JSON, right? All of it is JSON. And you can quite easily use a plain JSON parser and then interpret this yourself. It's not that difficult. But there exist existing libraries that do this for us that make it a bit easier. And so we'll use one of those. There are three generally available that are quite popular. So there's Tiny glTF, Fast glTF, and cgltf. The previous two are C++ oriented with templates and everything. cgltf is plain old C. And I'll be using that because it seems to vibe better with the rest of my code, let's say. It doesn't matter, right? Like at the end of the day, this is just at importing. The performance of this doesn't matter so much because we won't be using this once performance becomes important. We'll have our own format optimized to our own use case. But for now, this is fine. So I'll just build once. The C package has already added it because I already did that ahead of time, but just to be sure about it. So let's add a new class, call it model loader. And it says a new class, but it might end up being just a collection of functions. I'm just using this as an easy way to get a header and a source file. And we will include cgltf. Not sure if you actually need this right now. So, oh yeah, I am using GitHub Copilot for a very temporary time just to try it out, see what the hype is about. I've not used Copilot so far. Yeah, that's the kind of person I am. So let's get started. First things first, let's just call this function void. Oh, wow. That's interesting. But it doesn't understand what my file, or it does, or does it? It does. Interesting. Very interesting. It's not actually bad. Not that bad. I don't need all of that code too. Not sure if this is useful or harmful. I think I would have finished typing better. Anyway, load model, it takes a file name and it just does nothing at the end because we don't know what we want out of it. And as you can see, I'm not actually including anything here because we will isolate the cgltf to this part. So here I'll say cgltf and that's it, right? One header. We have to define cgltf implementation. Okay. Use that. And similarly, modular, we need a definition for this. Date definition. Okay. What's the fun with this? Like, this is taking away all the fun of my coding. Why do people use this? If cgltf load buffers. First you parse files, yeah, you get the result. The result is success. Then you load buffer, which gives you the new result. Result is success. Does not look nice. It's also not what I would prefer. Yeah, that's kind of it. And the errors SDL, log error, category SDL, log category. Is there asset? Custom? No. This is none of these. I'm just going to put it in their application. We'll eventually make our own log errors, right? Percent %s, comma, and do what string? So cgltf. Okay. Okay. It gives us errors like this, but let's check it online. Yep. Mm-hmm. Not equal to success, handle errors. Yeah. Seems like there isn't a reporting mechanism then. Loading, %s failed, or %s failed to load. Giving the results at pleasing. Nice. Nice puns. Actually, it's based on, like, originally the name was based on volcano, right? And there was this whole series of things that I had, like ideas. The API abstraction will be called Ember, then Blaze will be the rendering component, and then Inferno will be the engine. But what's the point? Yes, I am, but not like complete, let's say, feature complete engine, but to a certain extent, some features, whatever I want to use for whatever I'm doing, right? It's mostly to learn. I don't recommend making a game if you just want to make an engine. Sorry, I don't recommend making an engine if you just want to make a game. All right. So yeah, you free the data. I don't think it's supposed to be this free. Yeah, there we go. So you free it. Then we can load the buffers. Then again, error handling. Oof. I'm not certain I like profile. Settings, turn it off. That sounds better to me. If result not equals cgltf. I'm not a game dev by profession. I do it as a hobby. Professionally, I'm currently pursuing my PhD in computer science. Logger, still. It's a library for loading glTF files. You can just rewind a little bit. I gave a full explanation of what uh, this thing is, glTF is. So file and again, switch glTF data. Get part done with and you return. Like that. So buffers are loaded here. Okay. We're going to look at the documentation again. We don't necessarily need load buffer because this is automatic here. This is something we can do manually, but right now I'll just use it. That handles itself. What next? So next step would be to look at the data itself and we can see what's inside. All of that. Well, let's just go to it. Okay, so this is data. As you can see, all of these exist. All of these actually map to a reference guide thing within glTF. Oh yeah, I should put my code on GitHub. It's currently on my personal Git. I don't know if it's public or not, so I won't talk about it. I'll follow along. I might not actually watch any complete streams because again, I don't do this for education and I won't watch something that's not particularly education, but I will follow along and I'll make sure to see your progress. Yes. I'll keep in touch with you if you want. Now, so meshes is what we focus on first. So we'll first try to get all the meshes out of this. So mesh is, and there's a mesh count. So we can iterate through it. Actually, let's not. So the first thing that we have to look at is a node, not a mesh. And before that, we need to look at scenes. So we'll start with scenes. Data, scene, scenes. Each scene has an extension. There's a count of scenes that we have available to us. As you can see here, there's one default scene. Yeah, so there's a scene called here 0. So we'll take the default scene. For now, we'll only follow the default scene. Okay, they already loaded for us, so we'll just use that. I am going to rename the data to something like model or glTF model. Okay, so take it scene. The scene has a lot of data within itself, so let's iterate through that. There's name, nodes, and node count. Let's start with nodes. Normally, nodes are available as indexes, but it seems cgltf loads these nodes already for us, which means all we have to do is get to the nodes, get to the index of the node, and it will return to us the particular node itself. So let's get it. Nodes, and we want for actually let's take the scene out first. glTF, cgltf, scene, current build equals to glTF's model soon. There's a pointer. So now for current scene node count, so for uing32 till I equals 0, I less than nodes count plus I, each of these, and we move this in. Again, we don't need all of that, so it's just current sim nodes. And all right, so that will give us the exact node that we are currently looking at. Current node. Okay. Again, let's see glTF node counting. So what's current node? It has meshes. It has one mesh, possibly. Nodes can have zero meshes as well. It has children, which is already written into it, which is nice for us. There's matrices and all of that. We can look at each of these one by one. So right now, first I'll just take the mesh. Yeah. If it exists, because I don't know if mesh exists or not, glTF allows to have nodes without meshes. That way you can have multiple meshes connected to the same node. Each node has a particular orientation. So you can transform a node, you can rotate it, translate it, scale it, and every child node of that will automatically get transformed. These are known as transform hierarchies. Okay. So, I think at some point I should on stream look at Subedera's language. Might be actually interesting. I work a little bit on language design itself as a part of my research, so that might be interesting. Okay, well done. I don't particularly care, but let's continue on this here. So put it there. Current node mesh, fine. So if mesh exists, then we need the data from the mesh. Current node mesh. It will have primitives, and then primitives will have their own details and so on. So primitives, there's a count for this as well. So again, this we will take as primitive as a type. You have cgltf, primitives, pointer, primitives, then for u32t, equals 0 or less than. Oof, that's bad. That can be problematic. Node idx, node idx, node idx. Oh, he's using LLVM. Oh, maybe. That's pretty good. It's when they're actually send. So yeah, primitive count. So primitive index, primitive index less than current node mesh primitives count and plus primitive index. Right. So primitives, primitive index, that gives us these data. So each primitive has materials, has some attributes, has indices, and there's vertices somewhere in there. Okay, it's a part of attributes. So let's look at attributes. Again, there's probably attribute count. There we go. Show intensity, UT, I don't know how to pronounce it. But so cgltf attribute into attributes equals that. Then for u32t attribute 0 attribute index less than current primitive index dot attribute count plus attribute index and attributes, attribute index. There we have it, finally close to coming to data. Okay, I don't like this much nesting, so we'll start splitting this into, let's say, parts, right? So for each mesh, we will process mesh. We'll just call process mesh, which is a function that currently doesn't exist. We will write void process mesh, which takes a cgltf mesh as an input, then processes it. So we can write void process mesh and paste that here, right? So that becomes mesh. Okay, that gives us mesh. Again, here inside attributes, we have to take data, which is an accessor, which has all of these details. Let's see what's inside the buffer view. It's going further and further in depth. So what I will do instead is look at the spec for a second for inspiration. So accessor has a type, component type, count, buffer view, and we can then index into buffer views. Okay. So in accessor, we first need the type. We first need the name, really, because there are different accessors. Each accessor has. Wait, this is an attribute. Where are we? Okay, yeah. So for each attribute, there's a name. Depending on this name, the attribute will actually lead to a different piece of data. And therefore, we have to switch on this or if else. So I'll do an if. So if name equals, I think the first one is vertex. So accessor name is position. Yeah, attribute position. So we will look for position. So if it's position, it will give us some position data. String literal won't work because this is a car star. This is a C string. This is C++ string. So what we'll do is we'll actually convert this to a string view. String view literals are a part of C++20. I just need to include string view. You can check on it. String view literal C++. So that's string view. Let's check for literal. Okay, we need the string view literal's namespace. I hate when somebody asks me to manually use a namespace. It's sign of kind of not so nice setup, let's say. But now I can actually do equal to's because once you have string view equals, this will try to cast things into string view. Although I'll probably write it in the reverse, just to be sure, right? Left hand side is much better at picking up equal signs than right hand side. So you can see it there. Basic string view. Okay, so if it's position, then we need to grab the position data from here. So I'll just write it as a to do, grab, oh sorry, not this one, the others, grab other attributes. So right now we won't focus on the other attributes. We'll just pick up position and we'll see if we can actually model things with it. So, okay. const again. Let's keep things const as much as possible. It avoids bugs most of the time. So attributes, name, done. Now each attribute prim data is what we need. So attributes, attribute index dot data, which is an accessor, which has then count and buffer view. Component type. So we'll check the component type first. Switch on this component type. Again, we are mounting a lot of, let's say, for loops. So I will separate this part out. This will be write position, extract position data. Actually, I think there is a way to just do it using refactoring. So we'll do it later. Okay, we come here, generate the missing case statements. Now there's a few case statements. Component type R32F. Case. All of these are similar. We have scalars, we have vector types, but it's not a component type, right? That's a type itself. So we have to work through the types for that. This can be a little, let's say, work. Default, SDL, log error, category, SDL, category, creation, and we can say this is, the error is unknown component type. Component type. And we should be good to continue from here. Maxing them is not a valid one. It's just there for help as a helper. So we don't care for that. Type R8, R8U, etc., etc. Let's skip all of those and let's just consider R32, because floating point 32 is a common format, and we'll look for the rest as we come across them. Then for 32, we will start off with processing those. So again, we need to do switch case. So that's switch attributes, attribute index, data, component. It's just type. And now we have another set of types to handle. So default case. Hold on. I think it should be other way around. Types should come first, then component types. So we first filter by type. Invalid is invalid. Maximum is also invalid. Default. I think we can just assert false here. We don't particularly, like, if the asset has an issue, we can't really help it. The asset shouldn't be like having those issues, right? So assert false, and we'll say unsupported. We can always come here and check what was unsupported. We do the same here. Okay. Now, there's vector 2, vector 3, vector 4, mat 2, mat 3, mat 4. There's no way we could getting mat 2, mat 3, mat 4 as positions. We can have vector 2, but probably not. Same with scalar. We're not going to have scalar. So positions are mostly vector 3, vector 4. Anything else, we'll consider it as an error for now. And now that we have enough within this data, we can extract this. Let's see if that works. Defactor, extract method. There we go. Call it extract position data. Okay. And we shall say next. So that works out. That automatically creates this method, like function for us. Inside process mesh, we can actually give it the mesh. So current node mesh and call it a day, right? Alternatively, and possibly cleaner, would be to process the mesh directly and then inside process mesh, if mesh is a null pointer, so not mesh, return. So we don't process it if it's a null pointer. I think that's a cleaner way to handle this. Extract position data. Now we take all of this, but to be fair, it's mostly nonsense for this particular function because it only cares about the particular attribute. So we can just take it as attribute, right? And then I can rename this as position attribute. Okay. So that's it. Types that are not explicitly handled. Yeah, that is okay for now. Vector type 2, vector type 3, we need the data. So position attribute of data. We take the buffer view. So buffer view has its own data and everything. So we can take the data. I'm not sure how cgltf's buffer views work. So here you can see for box vertex colors. Actually, let's take the one we will actually test on, which is box. Box is the simplest model, right? It's just a box. So we will go here, glTF, look at the glTF, and we can see there's a single scene 0. So inside scenes, it will just go here. It will say nodes is 0. So we'll just take this node. There's only one anyway. Here, let's say children is 1. Okay, there are 2. There's a matrix, and then there's a mesh. Inside the meshes, there are primitives, 2 attributes, position and normal. So position is at index 2. So inside accessors, you go to index 2. Buffer view is 1. Component type is that 526, whatever that enum ends up with. They give us max and min values, and they give us a count. Okay. And with this count, we should be able to access things properly. Looking at buffer view, we have the buffer, we have the offset, length, etc. So they don't have the data here. The data is automatically loaded by cgltf for our use. So we can just take that into account, right? Let me check if the data directly has the values within it. It does not. Too bad. But anyway, so we have the count times size of vector 3, especially when it's a float. So what we can do here is we can say what type it is. We're not going to handle all of them, so I'm just going to assert on this really. Component type, assert, component type equals cgltf pattern this thing. If it's not true, then we can't do anything and we will have to test. We'll have to implement things later on. Okay, so data times data count times the size, which we can say is float. Size of float multiplied by its a vec3, which means that is 3 components. So this whole thing is the size of vec3. You can just say size p, size of vec3 size equals that. Make it a const to xpr. That's a permanent constant, yeah. Wait, 3 size. It's a compile time constant. The optimizer will take care of this for us. So count multiplied by vec3 size will give us all the data that is there, right? We will then mem copy this into some buffer, let's say. So I'm just going to call it a buff, right? I'm not actually putting the buffer there just now. Okay. We close this, and that's the size. The source would be just the accessor data itself. So we will say position attribute, the data, the buffer view data. Okay, so we copy from the buffer view data. If present, filled by extensions, we can check that. Insert buffer. I'm not certain. Let's check. cgltf use buffer. And it doesn't have details here. It asks you to just check the head of the glTF file. Let's check the head of the glTF file. Notation, options is to parse, structure is filled, wizard failed. We did the load buffers. Should validate it. We haven't done it yet. Accessor read index. Accessor read float. Like float, see the data into the accessor, applies parse data if possible. Saying, assume that your buffer has been called, passing well for the output pointer, users can find out how many floats are required in the current output buffer. This is it, right? That seems more like what we want. So let's see if we actually have things available for us that can directly do this. So data is the accessor. We don't need to look at the buffer view anymore. So based on the data type, just see unpack. We can just say unpack floats. We can give it the accessor, so position data float out. So we need to give it some pointer here. Let's give it a null for now. Float count. Excuse me. Where were we? Yeah, there it is. I'm just going to create a tab with cgltf so you can read this as we need. Reads data from the accessors. So we look buffer the count. We have called load buffer. Converts them to floating count, right? Pointing. You can find how many floats are required in that buffer. Okay. So this will just give it a 0 float count. And this returns the number of floats. So we can print this SDL log in. Can just log an error here for now. Log category custom. Why not? Okay. We cannot convert size to this thing. Of course it can. Percent LLU. So if we do process load model, if you do a load model, this would go to load buffers and all of that. We do need to test if this is valid. So cgltf validate the data. So that's just the data. Thing we'll call it glTF modeler. This gives us another result. So result equals that. And we can put the same stuff over here. If syntax is invalid, and here we can say buffers failed to load. percent s. All right. Build solution. Exact position, extract position data. It just takes the attribute now. So there we go. What's wrong with this? Attribute cannot bind to attribute const. Of course it can't. This has to be const. Okay. Now what? So float 3 is still there. Float 4 is another one. So we'll just add that here anyway. Or really just let it go down to assert. Build solution. Assert. Let's also assert on the other thing, since we already know what type we're going to encounter. We can just assert this being cgltf wake 3. And we can get rid of this. Okay. Whatever. We have load model. We should be able to just use load model now. Inside Blaze here. So we can put it at the init itself. Once model transfer and everything is done, let's load model. For model loaded, the file name was asset models box.glb. So unlike the glTF file I've been looking at online, I'm using a glb file here. Binary files just sometimes simpler. Hey, it prints nothing. Absolutely nothing. So what really happened? Load model. Oops. Okay, we'll start again. So we'll go to the debugger, go in there, we'll go over this. Result is success. Is it validated? It is valid. Load buffer, also success. Current scene. It should give us a proper scene. It did. Node index, it'll just have 2 nodes, no 1 node. So for that 1 node, we will process the mesh. Ideally, we should also have a process node thing, but right now we don't count it. So mesh is a valid mesh pointer. It was not a valid mesh pointer, so this doesn't do anything. That's the end, of course. Makes sense. What I did not do, what I should have done, is process node here. So process will take this whole thing, make an extract out of it. So refactor, extract method, process node. There we go. Instead of taking node index, it should just take a node. So current soon nodes node. It won't even be current soon. It should be glTF model nodes. No, I think it should work because cgltf automatically handles that for us. So instead of taking the CUJ, this thing we can take the node. Can do an ampersand, so that seems more accurate. So we don't have to do the current node there. Process mesh for current node dot mesh. Then for each children inside this, we will recursively have to call processing. So uint32t child idx equals 0, child idx less than node dot children count plus child idx equal that. And then we process node for each of these children, right? So that is node dot child children, take the child idx in it, gives you a pointer. We convert it to a reference because these are passed as if it's values. So we don't necessarily need to go through them as with pointers, right? The API uses pointers because it's a C API. Okay, now process node will handle it. This should print what we want. Something's wrong. cannot convert between node pointer and constant reference here, because nodes, it provides you a node reference, a node pointer. So build solution, start, node model, go in, step, 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 process nodes, go in there. We go to the child node in there. Process mesh will actually have something. There we go. So how many primitives do we have? Primitive index, primitive count is 1. So there's only one primitive. Attribute. So the first attribute will be normal. So this should get skipped. Second attribute should be position. So we go in there and extract position data. Do that. cgltf unpack floats. So this should print out some value to us. Answer is 72. Now the question is there actually 72 floats in this box? This is the same model. I only downloaded it ahead of time and I downloaded the GLB version of it. It says here that buffer view has byte length of 72. That's buffer view 0. Positions are in buffer view. So position is in buffer view 2. So attribute 2, sorry. Attribute 0, attribute 1, attribute 2. Buffer view 1. So this buffer view. Byte length is 576. Okay, that's big. Next. This one, count is 24. So that checks out. 24 times 3 is 72. These are vec3s. So the number of floats is in fact correct. So let's get into this. Unpacked floats. We have to provide it a buffer to unpack into. We will dynamically allocate for now. So all of this is free to do dynamic allocations at the moment. At some point, this will have to be like reallocated, let's say. Yeah, I'm not sure I want to dynamically allocate it either. So, okay, what I can do is I can take the global memory here, global memory pointer mem. Okay, so node memory here moves that as well. Stop global memory. Global memory const. Well, it's sort of const, right? Just a pointer. All right. Now here's what we're actually doing. This load model will take the memory first. And inside this memory, based on all the remaining memory, so I'm assuming nothing else is working in parallel right now. I'm taking all the remaining memory and I will create an std_pmr memory resource. So what is std_pmr? It is polymorphic memory, memory resources. So effectively what you can do is you can say, okay, std_pmr, not a specific memory resource, but we will use a monotonic buffer resource where it will take a buffer. So here we will give it mem dot. So we won't allocate directly. So we'll take the state first. We don't necessarily have to. This will automatically handle this state for us. So monotonic buffer resource mem dot memory, comma, buffer size, which is nothing but mem available. So we give it everything and it's able to use all of it as required. That's the buffer resource. Okay, I need to name it. Let's call it MBR. Okay. So what happens is now this becomes an allocator, this monotonic buffer resource. And so this can be just provided downstream to anything. std_pmr polymorphic allocator of type, again, std_byte. which is default, so we don't have to. EMR, and we can create it from a memory resource. So we give it NBR. Okay. So, or allocator really. So this is a standard library allocator that will automatically help us do all the allocations that we need to do without us having to deal with anything. And so for nodes, for this processing, we can just provide a single buffer called vertices. So we can say std PMR vector. So that comes, there's an std vector with a PMR allocator that has float threes, or so DirectX XM float 3. So that's the float 3 variable. And we call it position. All right. So now this will just buffer, like this buffer will just be filled up with positions as we go. So inside process node, we will pass this in. So we will say positions. We'll pass it to a pointer because that is the rule. I'll correct it, clean it up later on. Right now, we're just doing it because we want to be clear that this is being passed. So fix it. You take an std PMR vector of type DirectX XM float 3 positions. There's a pointer just to tell us that we're going to write to this, right? Now, what I can do is I can do a little bit of a, no, never mind. You can do a using that just templates it up. Like, this just renames this to make it something easy to see, but no real point doing that. Positions. Okay, process mesh should also take positions. So positions, and we'll need process mesh to also be using these things. So there we go. With definition, add it there as well. And so now what we can do is inside extract position data. Again, we'll add the positions here. Oops. Positions. And inside extract data, again, we'll add positions there. So here, when you unpack the floats, you should be able to write it. What we do is we get the size from here. So size the float size equals this. Once you have the float size, we can take the positions, size. It takes the new size, which means it's positions dot size plus the additional size we'll add with float size. So float size, but this has to be divided by 3 because we're using vec3s because of this. Okay. Once that is done, float size, so positions have been resized. We also need the back for the position size. So we cut that. Per size P. Per vertex start. Vertex start plus that much. And now that we have vertex start, we can just write to that location. So we can say cgltf accessor unpack floats position attribute dot data. Instead of null pointer, we can give it an exact location. So we can say positions dot data plus vertex start, right? So that gives you the index that we start at and the float count, which is the additional size we added. So float size. Okay. We will rename this. It's a float count. That's more accurate. What's wrong with this? So float 3 cannot be cast to float, not with that attitude. So there we go. We have cast it to float. Resolution. One failed. Load level does not take one argument. Of course not. It needs a mem. Making a CPU based on the Subedara instruction set, including 4 registers. Can you tell me simple logic of RAM or ROM? Depends. What do you mean logic? And it depends on what you're doing, right? Like, so if you're emulating a CPU, you can skip in emulating the RAM and simply consider it as an array that you can fetch from, because generally there'll be an integrated circuit that actually addresses the RAM. If you're doing it in Verilog, then I have forgotten how to do that. It's been a long time since I've done anything like this. So it's G memory. So with that, we pass the memory in, showing into app state here. Okay, so now what? How to code it? Start with a like array, right? So RAM is nothing but, let's start with a simple RAM. Nothing with like virtual memory, no paging, nothing. It's a simple array of memory locations starting from 0 going up to whatever you want, right? Each address is nothing but an index in the array. That's what a RAM is, until you add more complicated stuff like virtual memory and all of that. That you can check how paging works. You can read up on it. And that's all you really need from, you know, a RAM. It's just a way to fetch data from something. Oh, did I go too far? Let's see position. So size is 24. That is expected. The data seems to be correct. Okay. So that is exactly as we expected. This color theme is an amazing one known as Visual Studio Dark Default theme. If you have Visual Studio, if you use it in dark color, this is the theme. uh, it's right here. So tools, theme, you can see this is dark plus. It's built in, it's a default one. This is the basic dark. Why was I using dark plus? Yeah, it's just a barely different color. Yeah, Genie is nice. So I use Visual Studio here for this thing. Most of the time I use Emacs. It's just that recently Emacs hasn't been very good on Windows. But at work, it's always Linux, so it doesn't matter, and I use Emacs everywhere. Yeah, this is Visual Studio 2022. Okay, where was I? Cool. So we have unpacked the floats. We're able to write to the positions. We have a vertex start available here. It's not doing much right now, but we'll get to it. So we've done positions. We've said it's extract position data, but in reality, it's just extract data, right? So we'll add that in. Actually, let's not add that in just yet. So let's go to model loader again. What else do we have in model loader that we actually need to take care of? So we need a model at some point. So struct model. What will a model have? So it will have a set of nodes. So we call it a node. Okay. This will be a vector of nodes or a tree, more or less a tree of nodes. So we'll just say node, node. Similarly, nodes would be struct node. What would a node have? A node will have a transform. Forward declaration to a transform. That doesn't work out for us. So I will actually add a secondary transform here, perhaps. Struct transform. Okay. XM float 3 indirect X that include some math library. We need it everywhere. Position direct X. So I'll actually call it load transform just to keep it separate from everything else. XM vector quaternion for rotation. I will store it as an XM float 4 because XM vector has a requirement on alignment that I might not actually be able to handle right now. Scale. It's a uniform scale right now. Cool. So that is node transform. It's just this data. It's the same as the one we're using in the entity, but we're keeping a separate struct for now. We merge it soon enough. So model takes a nodes, a set of nodes. Nodes are nothing but a node transformed, and the mesh. So mesh, again, there is a pre-existing mesh class, but I'll add one here. So struct, model, mesh. These are temporary. All of these are temporary. These are just experimentation, right? Model mesh. If it has a mesh. So not every node has a mesh. So that's a sparse one. What else would we need right now? So the model itself should have a vertex buffer associated with it. So I'll just create an std vector. Okay. This vector will contain all the required vertexes, which are right now just XM float 3s, because we only have positions. So vertices. Okay. The allocator needs to be kept alive. So that will be stdpmr and polymorphic allocator, or really polymorphic resource. So memory resource. In this case, that's a monotonic buffer resource. Okay. So inside monotonic buffer resource, what do we put in? Nothing for now. This is a default type monotonic buffer resource. We'll call it mem. Okay, architecture of this model is going to be a bit interesting. We can have these models as completely separated entities that are each independently handled, that are parented under the same node. Or we can have this model as a separate class in and of itself and, get the system to sort of deal with it. I'm not sure which side to go with. I'll think about it after today's stream. But for now, I'll just use this sort of a nested model representation that we will convert into entities after the fact and render it. And because we're not really doing much with this, it's okay for now. We can later deal with things as things are. Okay, so that's a model. We want the model to be returned to us. We will do a Boolean here in case there's a issue with the noding. And we will put the model as the first thing. So there's a model pointer model. Okay. So this has to be changed here. So that becomes bool model pointer model, and we're good to go. So inside load model, return false, model loading failed, false, model loading failed, again false, model loading failed. Hold on, don't we use pointers that I've returned from here normally? Yes, but this might be temporary, so I'm not going to. False is done there, process load here. So this takes, as you can see, this takes XM float 3 positions. We provide all the data to this buffer here, to this MBR thing, which means by this point, there is nothing left for us. Ooh, I made a mistake here. So let's connect that. I forgot to pass the allocated. Okay. So instead, what I will do is instead of giving it all the available one, I'll give it something like 128 MB. I don't think it's going to need more than 128 MB, right? I can't give it 128 MB. My entire memory is that much available by two. Okay. I give it half of the available memory. The latter half. So we give it some part of the data that we don't particularly care about, and we use the remaining. So temporary data is separated out so that this vector, which will eventually go on the permanent data, doesn't have any issues. So now that the positions have been allocated, we can just copy them into the model. So the model just to be allocated on the memory itself. So mem allocate size of model alignment. So align of model with both of these, that gives us some memory. So that's std byte pointer allocation equals that. And if not allocation, then we return false. If allocation is available, then we new allocation model. Does it really have a constructor? It does. So first is mem. Mem takes it needs an MBR. Unfortunately, we cannot really provide it one straight off the bat. What we need to instead do is calculate how much space we actually need. So what we will do is take positions.size. I know this is like needlessly complicated. I could just allocate everything on heap and get it done with. But it's a matter of principles. Data, size of pointer. Okay. So that takes the size of this data. And then I can just say this is the total size I need. Hello. MBR size, right? And now MBR can be like a new memory buffer resource can be created. So to do PMR monotonic buffer resource, which is MB permanent. So block, let's just call it block, which takes MBR size and does nothing with it. Okay. This size, since it has to be given to this, I have to do allocation always again. So mem allocate, and we'll give it MBR size or my MBR size. So it's going to pull from this memory. New vim's nice. Evac is superior. No, and let's not get into that. To each their own. So then we can just add this. So block nodes are nothing right now. Vertices are this allocation that we create, not allocation setting. This positions that we still haven't done. So std, emr, vector, directx, xm float through. So I'm not being very optimal here. I know that. Not being very optimal here. I will eventually optimize this, but right now I just want to get things on the screen first. It's not DirectX, it's just the mathematics library from DirectX. If Yeah, we did take model from outside, so model actually exists already. So we don't need to particularly do an allocation on the block here. So this actually just becomes model and it should be able to handle itself. All right, now what? So MBR size can be made const. Sure, let's do it. Final position can be made const. Yeah, let's do it. Final positions, I think it can, but I don't have to. STD ranges trans. See ranges transform, and we can just take the positions, we output it into STD back inserter there, back inserter on the final positions, and we actually don't need a transform. We don't need a transform for auto and DirectX. Don't even need that. So final positions dot resize, and the size of the positions dot size. It's in cost qualified. Oh yeah, hey, my bad. So final position has been resized, and then for mem copy or std copy, first position, so that's positions dot begin, positions dot end, and out destination is nothing but positions dot begin. It will just copy their locations. Yeah, why not use ranges dot copy, right? Cool. So that again copies everything. So we have our vertices. Now we need to create nodes. Assess nodes here tries to create nodes, but it doesn't actually have anything here. So stdplr, vector, directx. Let's make a node transforms or nodes. You can take a we can't necessarily take the yeah, we can't actually take it like that. We do have the MBR, so we're free to allocate things as we should be good to go. When you don't code, you want someone else code. That's reality, isn't it? Us coding maniacs. We don't have anything else, eh? Positions. We're not a like preferred resource. Perhaps I want a different resource there. Tool. There's a pool resource. Again, this is not a tool resource either, so NBR is fine. Perhaps I should give it only 1/3. The last 1/3, let's say. And then you give unsynchronized pool resource the 1/3 before that. Oops. What's wrong with you? Yep, yeah. What does it take? Pool options. So let's create pool options. STD, PMR, EMR, pool options. max blocks per chunk and largest required pool block. Max blocks per chunk. Gosh, why am I doing all of this? I'm overcomplicated things. I'm overcomplicating things, my bad. So we keep MBR as it is. We don't particularly care. It's just going to allocate data on itself. We create nodes. So node root. I put the game engine half as a, let's call it a, what's the word for it? Where you put a fake headlines? Clickbait. Yes, clickbait. That's the right word. It's a clickbait. I'm not coding a whole engine. I'm coding only the parts of an engine I need in order to have something working, let's say. So node pointers, node pointers, but process node will return. So here I can say root equals this. Root can be an stdpmr vector. This is likely wrong code, right? It's likely wrong. I don't particularly care at the moment because we just want to get things on the screen. So I'm even going to remove that. I'm just going to pass the nodes in. So nodes, right? And yeah, just put that. So this is supposed to be PNR. Vector nodes. We'll here end up with again the NBR with the allocator. And yeah, so this nodes gets passed in. Okay. Inside process nodes, we will take positions. We'll also take the nodes. So stdpnr vector nodes. It's a pointer. So nodes here like this. Takes the nodes. Now we process nodes. Every time we process nodes, we have to add nodes into it. So here we'll actually do the processing for a node. So what do you mean the processing for a node? When we have a node in cglTF, it has a given matrix or a set of translation, rotation, and scale. What we do have to check if whether it has a matrix or translations, rotations, and scale. The question here that we end up with is, does cglTF automatically add translation, rotation, and scale? Probably the answer is no, because mostly you would leave it to the user. So if node dot has matrix, so if it has a matrix, then we have a matrix and we have to deal with that. So there, node dot matrix, and then we have to do a, let's say, recast of this, reinterpret. So we'll take directx xm float 4, a 4x4. So it's a matrix. Mat is equal to, and we construct it from this array. Cannot resolve. Why not? Self float 4x4 right there. Did I make a mistake before? Anyway, so this is explicit constructor that it needs. So we'll do that. directx xm float 4 x4. I think I made a small one. So node, that's it. We construct it from there. So that's the matrix. Now we need to do a decomposition. xm decompose. There we go. It needs to give out the vector, the rotation quaternion, and the translation. Let's see if this is xm vec matrix. Can I construct that? xm. Do you have a renderer set up yet? Give me a sec. Something failed compilation. 1 second. Syntax error on this, of course. Build. I'll have to convert this initializer list to model because lem can't take the block. Tempted or deleted constructor. Yeah, that checks out, I suppose, because you can't copy a memory resource. It has to be moved. Movement doesn't work either. Okay. If you say so. In that particular event, we'll have to deal with it differently. So model.mem, no, not really. So we have to take this lock. Sheesh. What do we have to do for this to work? Can check. std tmr move resource. Ah, screw this. Screw this whole running buffer resource. Right. Uh, we remove that. Let it allocate on you. I can't be asked. Okay. It's going to work just the same. But anyway. So build once failed again. MBR is created but not referenced. Fine. Mem is an unreferenced resource as well. I can just do that for now. Failed again. Load model. Yeah. That will be the reality of this, right? I just want something on the screen. Why am I bothering optimizing it ahead of time? Premature optimization, because mostly allocation is not that expensive. I just want to keep allocators in order to keep it local. But all of this data will no longer be used after we copy it into GPU. So why do I bother? Okay, build again. Yeah, so did you ask me if I have a render set up yet? I'm missing debugger. There we go. So I have texture set up. I have meshes and a general way to sort of show it on the screen, have transforms and everything. What I don't have right now is a way to import meshes and a convenient way to set up vertex buffers, let's say. Because right now, independently, I'll have to make each vertex buffer for each model. But once the whole bindless is complete, everything will be in the same single vertex buffer that will be globally shared across all the models in the scene. And we'll just like allocate, deallocate from that one buffer. It becomes far more optimal to use when you stop having to create separate buffers. Anyway, coming back. So models, there we go. Load models is fine. At the end, we will return true. What is remaining? Yeah, so we were doing this. Matrix decompose. What does matrix decompose do? It takes an outscale vector. So directx xm vector transformation. No, it's translation. Translation, rotation, scale. And we give them in. So translation. It takes a scale first. Scale, rotation, translation. And it takes the matrix, so as mat. Now here I'll also add another thing, which is I'll say translation is fine. The rotation should be Q rotation. It's a prefix that tells me this is a quaternion, just where I don't forget. And I'll ensure that I do this more often, right? That can be made constant. Why not? So this decomposes it. Assert. So I can directly assert it. This should always decompose. It's a part of the specification in glTF. So any valid glTF will always ensure that decomposition works. Then translation rotation can be moved outside because translation equals directx xm vector, and we can pass in node dot translation. And here I'll have to say if has translation. So I'll do it. I can do it here. So if node dot has translation, do node dot translation directly. What's wrong with this? It's float 3. So we have to manually do that. One. Okay, that should create an XM vector for me. DirectX XM vector. Do we have a built-in sort of way to handle this? We do not. Why does it have so many variables? Node float 4. Okay, that's one thing. And secondly, sem vector set. I'm more comfortable with using the vector set for this. XM vector set node. So there's no translation now, so we'll just say it's at origin because that's the default value for this. Okay, that sets up translation for us. We'll have to do the same for Q rotation. Again, node dot has rotation directx xm vector set node dot rotation 0. This time it is a float 4, so we should be able to conveniently write it. If it's not a valid vector set, then it has to be a default quaternion, so xm auto layer identity. So that way we use a helper function, which is quite nice. There is, I think, a vector set, vector 0 as well, but because we have this 1.0 here, we can't really use it. Okay. And lastly, we have to take the scale. So scale equals node dot as scaled question mark directx. Again, the whole dance and so node dot scale 0. And the last point is 1.0. It doesn't really matter. The interesting thing we are going to do on the scale is more important. We actually won't get the scale out of this. We will instead assert scale 0 scale dot x. You can't do scale dot x either. So x directx xm float 4 node. Xm float 4 takes, wait, hold on, that's the wrong. As a constructing it takes a vector, it does not. Oh, how do we undo from a vector itself, huh? The matrix decompose definitely takes vectors. So scale dot, we have to take it like this, I suppose. So 0, that's the scale. So this is equal to 1 and equal to I can say 1 is equal to 2. And I don't even care about the fourth one, right? Because there's no 4 dimensions in this clearly. Assert and non-uniform not supported. Okay. So we don't support non-uniform scaling at all. All we have is a uniform scaling, which is uniform on all dimensions. So if it is uniform scale, we say scale equals scale dot. Oof. Scale 3D, scale 3D. Actually, it's a 4D. Okay, make it V scale. V scale, V scale, V scale again. Should have renamed it instead of doing this manually like this. So V scale, we just say F30 to 0. So all I'm saying is that the scale is exactly the first value in the sequence. Here, again, scale equals, in this case, I'll have to be an if again. So node dot has scale. So if it has a scale, then we have to do the checking. So node dot scale 0 equals, copy this. I can say, copy that, paste it here, remove. So let that scale equals that. Which is equal to that. Okay, now if the scale uniform scaling is working, we will then, just assign it. So scale equals node scale, node scale 0. And else, so I don't think I'll actually get the model importer complete or even rendering parts of it today. I already feel quite, let's say, sleepy. So I might have to go. But otherwise, scale equals 1.0. Alternatively, scale equals 1.0 ahead of time. And we don't have to do this. All right. So now we've got the rotation scale and everything. We have to find out. Keep those as they are. We leave this whole thing as it is. Copy that into the translation. Q rotation. Q rotation can come out directly. V translation. And translation equals V translation dot this value. It's an explicit constructor, so we say direct text xm float 3 and just let it handle from the pointers. So it'll automatically load the translation for us, which means here life becomes a little simpler because if it has a translation, we can just say xm float 3, give it the node, let it handle, load the translation, let it handle the loading. Else, it is just DirectX xm float 3. It doesn't take a 0, but there's an xm float 3 identity. There is that. 0, 0, 0. Fine. It's easier to write right there. All right, moving on. All of that is done. We have all the data we need for a nodes transfer. So nodes pushback. So it takes a node, but then you do an emplace back. So it takes the constructor arguments. Inside a node, what do we have? So inside the node, we've got the transform and we've got the mesh pointer. So we'll do the transforms first. So we'll create the transform, node transform, which again takes a position. So we have that as translation. Takes the scale. So we have that as a scale. Takes the rotation, which we have as a Q rotation. I leave it as the Q rotation because I'm going to go back and change this to Newtonian. So here float vector. Doesn't make sense to leave it as anything else. So Q rotation is done. So that is transform. And now we need a mesh if it has a mesh. So this one will come from process mesh. So here I'll just say process mesh within the creation, or perhaps do it ahead of time. The mesh pointer, mesh equals process mesh. We take the mesh here, we pass the mesh in this, and at the end of it, right? The mesh can be, I think we call it node mesh, the model mesh. Gee, why am I creating so many weird names, eh? Process mesh should return the model mesh now. Pointer to model mesh. It has positions, it has nothing else. Should it return to a model? It should just return a model mesh, not a pointer. Okay, so we put a model mesh here. Let it return a model mesh. If we pass that in there, node transform, make it a model mesh as well. And model mesh is empty. So that's why I said here we can take model mesh here. So we enter E2T and we'll just make it pure data. So vertex start. I'll come to it again, what vertex start is. But effectively, you're just taking the starting point and vertex count. So you start from that location and you do it for as many as count. This model mesh is nothing but a set of primitives. And it will load as the primitives load inside the mesh itself. So let's continue. You might have to add a vector of them, but we'll come to that in a sec. So if a mesh has 0 indexes, we just skip it, right? That's the simple way of handling it here. So node transform, that will process it. This will continue. All of that is fine for now. Next comes process mesh. If not mesh, you return. Instead, you'll return something with 0, 0. So that's the default. We will extract position data here. So this position data, as you can see, is a set of primitives. Each mesh has multiple primitives. So each of these primitives needs to be separately written inside the mesh. So we go back to the model mesh. Vertex. So there's a vertex start and vertex count. This actually becomes std vector of vertex counts and std vector of vertex starts. So much. Now, go in there, process mesh. There's an extract position data. We do primitives here itself. So what we can do is we have the vertex start from this. We should also get the vertex count. Size p const vertex. We have it already. The float count, but vertex count is just 1/3 of it. So we calculate that here. So what I'll do is I'll just say calculate ahead of time. So size p const vertex count equals the value vertex start plus vertex count, and that's the right resize. It will copy the data here and it will return us a vertex start, vertex count. So this, when I optimize it, I might do it off stream because, again, as you can see, there's no real point. It's all grunt work. So there's no real point of me sitting here and doing this because there's not much I can explain with regards to what is happening. Extract position data returns a pair, which is start, out. And then we can give the start, count, and we can push it into the current mesh. So we can say model mesh. It does no start time. Oh yeah. Rect mesh or out mesh. Okay. So now for outmesh, we can start doing this. Outmesh dot vertex start dot pushback start and vertex start dot so outmesh dot vertex count, and we add the count there. Cool. So this should be able to print all of those in. At the end of the whole array, we return the outmesh. All right. Build solution. Seems to be fine. What next? So it's trying to convert from a size t to ty, where ty is unique pointer. It's happening within this. So this is unsigned ints, while the pushback is taking size t's. Is it? No, it's even 32s. It's a tuple thing. So model mesh extract position data returns even 32s. These are size 2s. I will take even 32s for now from this. It might be a little buggy, but that is kind of okay for us for now. We'll manage costs. Okay. All right, that should return to us this model in a very crappy sort of setup. Again, node gives us a node, takes a pointer here. Instead, let's return a single node, the stud vector of nodes. Okay, and each node itself will have a stud vector of children. Dynamic allocation. No. So now nodes can become an array here, which is nothing but this process nodes. So each process nodes will take the vector of nodes and push back a node into this vector. Okay. So if the node exists, it places back. Otherwise, it processes the other nodes. It takes, instead of taking nodes, it will take node.children, not nodes.children. This particular node, so nodes back dot children dot, no, it's just a reference to back. This expects a PMR, while nodes use a non-PMR vector. This has to be PMR. So you have to make a choice at the start of any design. Will you use polymorphic allocators or not? So polymorphic is the PMR. If you will, then everything has to be PMR. If you don't, then it can be all start pointers, start vectors, but then allocation is going to be a pain for you. Like customizing your allocation is going to be pain for you. Right now, it's going to be very simple because I can just pass the allocator and all of these will just work. Like the types are fine. Okay, coming back, this happened node vector, node vertices. We are fine for that. So loading the model right now returns, it gets us the model here. Let's go to the CPP file here. So we do the load model, we get the model, and now we need to create entities. So app state dot entity manager, create entity. Now what does this entity use? First, it uses the model transform, which we don't have available directly because model dot, you can see there's like a weird set of things. So instead, we will have to do for model dot loads. So for each node, auto and node inside nodes. We will take node dot transform, which is a node transform. We will change this to the entity transform itself. So we'll import that. We won't use this anymore. The details are the same for entity transform and node transform. So this should just work. Okay. So we take the node transform and we say entity app state, entity manager, create entity, takes the transform, takes vertices. It takes a span of vertices. So model dot vertices. So that takes the span. And then texture file. We'll just add all of our texture files for now because we haven't set up like loading for texture files and all of that. Nor have we set up like a proper texture system that can just take a texture instead of a file name. Anyway, what is this doing? So it's trying to take XM float3 and trying to convert it to vertices. We don't have vertices set up for this. It's expecting this sort of stuff. So what I'm going to do is I'm going to take this. I'll make an std vector node dynamic allocation vertices. Okay, then vertices dot pushback or emplace back more like emplace back positions for auto and pause in vertices from there. We take vertices dot emplace back. We say pause dot. So just take pause. Color becomes XM float3, some random color. We can have it be 111 light color, which means it will just take the color of whatever's underneath. And we take the texture code of just pause dot x comma pause dot y. Called with 3 arguments. Actually, for color, I will give it pause as well, right? And this one is dot. Okay. What's wrong with this? Emplace back has 2 parameters, but is called with 3 arguments. Okay. Vertices. So vertex has 3 things: position, color, and coordinate, texture coordinate. So here it's taken with 2. Here's the pushback, vertex, position, color, and text coordinate. That looks about right. So that pushes all the vertices into this vertices. And we rename it to words. So it changes to this words. And then we pass the words in. Okay. So what is about to happen is that we will have a queue with no transforms on it. Because there's one node with the transforms and then one node with just the queue. Something failed. Node transform is an undeclared identifier. Yeah, because we did an emplace back. Why did we do an emplace back on node transform? Okay, yeah, makes sense. That takes a transform and we don't have the cube being drawn. So what happened to the cube being drawn? Well, it's the time to debug. That is a simple one. So we take all the nodes for the model and we push it as an entity. We don't do it for each of the child nodes. So now what I'm going to do is I'm just going to say auto push entity. Again, I'm not claiming this is good code right now. This is absolutely garbage code, okay? So beware. Node and it takes a node. So that's a push entity. And for each of these, I will push entity and take the node in, okay? And within this thing itself, after you create all the entities for node children, so for node dot children, auto and child node children, I will push entity child. So it recursively will add itself. And I've used a lambda to do this. Cannot convert a lambda to an integer. Why is it asking for a lambda to convert to an integer? To term does not evaluate a function taking one argument. Function void mode. Sometimes you have to do this. I don't know if it will work. Okay, it did. Still doesn't work, eh? Just check what's happening. Didn't even stop. The debugger, it never went in there. So we'll go here and check what's happening. It didn't even go there. Didn't say model has any nodes. So model has no nodes. Why is that? Take a model, see the model, it has no nodes. Go in, all of this is fine. We return out. What does the model have? It has no nodes. So at some point we forgot to assign nodes into the model completely. Let's see this node model. So process mesh, that is fine. Process model is up there. Says node. Node totem place back. This is fine. Sheesh. I'm having like the most chaotic stream I've done so far. And I have the most number of views I've had. What the hell? Okay. So nodes enclase back. So you do enclase a node here. This is nodes. Nodes comes from the process nodes input. Fine. Process nodes gets his node input from here. That is fine. This is the model. And yeah, there we go. Skip that. It is pushing entity, so skip that. It hit a breakpoint. Something happened to the creation somewhere. Okay. So when does this happen? This happens when there's an issue with like the loading of a system here. All right. So let's look at what I like. What do you mean by, sorry, not loading of a system, but like just drawing the entity where it happens when there's a problem drawing the entity. Cool. So this is the first entity. These are one of our like 7 basic ones. So 2, 3, 4, 5, 6, 7. Here's the 7th entity. This one is 4. So yeah, this is the same one. Continue. Vertex count. Okay, what happened here? What's our vertex count? You go into command draw. It tries to return your mesh. Commits the mesh. The mesh has a vertex buffer size of 768. So this is the right one. This is the one we're looking for. We go up one step. And this should be able to draw. So generally speaking, all of this should just be able to draw. Okay, it did draw. But it's not drawing the cube that we wanted to draw. Plus, it seems like there is an error. So configurator, and we can check. Okay, there's no validation errors. But the mesh is still not rendering. So what's wrong with the mesh? The answer is that we're not doing the primitives. I mean, no, it's not really the answer because there's only one primitive and it's all of the vertices in it. Problem is probably the fact that this entity is sample mesh here has first, which has no matrix, so which has a matrix of this value, but then second it has nothing. So if I go back and start again with a debug point set here, so if we look at entities, right, entity manager, you see entities, count is 9, fine. So this is the first one, second, third, fourth, fifth, sixth, seventh, eighth, and this is the ninth one. This is the last one. This is the one that we are interested in right now. So you see the transform, the position is 0, the scale is 1, and the rotation is this like weird quaternion value here. Is this even a correct value? Yeah, seems like it actually. So why doesn't it draw? There's one more. Let's return this thing to the vertex buffer. Vertex count is 4. Run it. Run. Run. Oh, it's the next frame. That is running. It's giving us this. For some reason, it seems like the additional entities are not just not being drawn. One possibility is that we're culling. We're not even culling. Culling is off. So we can't be culling it. What else can we be doing? So let's try something. Let's remove the texture index. So here we try to pass the texture with the push constraints. I will pass just 0 here. So I'll just say instead of this, let's pass offset, which is 0. It's not the right size, but it will work out. So this will just paint colors. Okay, that is just fine. So let's use RenderDoc. Let's see what's up with the particular thing using RenderDoc. RenderDoc is a nice graphics debugger. I'll build it once because RenderDoc is going to pick it up. I have it set up here for my application already. So it captured the first frame. I will capture another one. So this is the first frame. Now what's happening? Color pass. You see there are 224 command draws. It is going to, so if we go to vertex shader, the mesh viewer, we go to vertex shader, we can see the output. So here, position is 0, like all the positions in the vertex input are 0. All the positions in the vertex inputs are 0. So yeah, it can't draw anything because everything is 0. It shows up as 0. So no crap, like it literally can't draw anything. Fine, so let's see why it's zeros. We load it inside the model loader. Vertices, final position, that's fine. Range copy positions.begin. It's the output. And as the input, it takes an XM3, it takes an XM3. Fine, that much is okay. Positions here. Do they actually have values? Positions is 24 and they do have right values. Positions.begin. Let's try that. Aha! There is the issue. So very dumb issue. Here's the box. It's not much of a box. But it is a box. Some weird stuff are happening with it. It is not entirely unexpected. So For one of these boxes that are being rendered is the first matrix. The first matrix rotates the box probably to a different dim. So if you look at the value, you can see it's a 1. So this is just 1, -1. So it's a transform that is actually going to rotate things. Okay. So it is rotating. And so what we're seeing is one rotated version of the box rotating along its own axis. And since we rotate along the local y-axis, it's 90 degrees tilted and it's rotating along that y-axis. That's why it's rotating like this. The one in the front is rotating in the correct, it is the expected direction, like everything else. But the reason we see it so glitched is because we have no concept of a depth buffer. So all the rendering is occurring in the order of operations. So the side that is currently at front is rendered after the other sides. And because of that, it appears as if it's always at front. So even if it goes back, it appears in the quote unquote front. Okay, let's go back one sec. And since we already have the, let's say, position that were being copied into the entity around here, yeah, we change it to 0. That way we can see the texture itself. The interesting. Yeah, it's not supposed to be 0, it's supposed to be 1. Because it will still multiply with the color, and if the base color I give is 0, then it multiplies with 0. The color becomes black. There we go. So you can see now clearly that this side, I don't know if you can see my cursor, but the side that I'm pointing with my cursor always appears on the front. And since we are mapping XY, the other sides are just like fit at the same coordinate systems. This will have to be fixed by loading the UVs and the normals and all of that. We haven't done that yet, but so far, at least we know how cglTF operates, let's say. And so next time on the next stream, what I'll do is I'll actually get a proper way that I'll store my models in. And once I know how I'll store my models, I will work on how to render them. And another thing I'm considering and probably will end up doing is to merge the entire model system with entity. So each model primitive, each node will be an entity in and of itself. And we can have a parent-child relation within the entities in the main world itself. So that way we can automatically do the transformations and everything. Then this is all left to the next stream. Thanks for coming. It was fun having you around. A lot of conversations today. And I hope to see you again. Next stream will be probably tomorrow. Yep. Next stream will be tomorrow. Have a good time. Enjoy. And see you in, let's say, around 20 hours. Cheers.